Hello, students. So, how are you all? I hope you all are doing good. So, we are back with the series of lectures which we are doing as a chapter of heat. Okay. So, we have already done 2 lectures of chapter heat. So, in the previous chapter, what we learned the modes of transfer, or I can say modes of heat transfer. Okay. So, we basically learned 3 modes of heat transfer there. One was conduction, another was convection, and third one was radiation. Okay, and we already learned conduction and convection requires medium for heat transfer, while radiation does not require any medium for the transfer of heat. So that we have already learned. So now we are into the last lecture of this chapter, heat transfer. So now today what we are discussing, let's see. Okay. So today what we are going to study in the last topic is the 2 new terms. Okay. 2 new terms we will talk about. One is specific heat and another one is known as thermal conductivity. So today we are going to discuss about these 2 new terms, specific heat and thermal conductivity. Okay, so ready to learn? Yeah, ready to explore new terms? Okay, so let's go. Okay, so suppose if I take an example, suppose you are having a beaker of water. This is a flame beneath it. Okay, this is a flame. So what I am doing, I am taking a bowl of water. This is a bowl of water. I am putting this bowl of water in this. So this is kind of small bowl of water present in this pan. Okay. Now try this, or try to heat this water. Try to heat this water for 1 minute. Try to heat this water for 1 minute. Okay. So what will you observe? You will observe that in 1 minute, it will get boiled. In 1 minute of time span, it will boil. Now what will you do? Now put more water in the beaker and fill it up to the brim. Take more water in the beaker and fill it up to the brim. Then what will you observe? If you again heat it for 1 minute, then you will observe the temperature of water is not raised as in the first case. Suppose in the first case, the water was boiling at 100 degrees centigrade in 1 minute. So in the second case, when you have filled the beaker up to the brim, the temperature was suppose like 60 degree only. So from this, what can I say? What was constant here is the time. Okay. What is constant here is the time. What I have increased the mass of water. I have increased the mass of water. So can I say in the first case to increase the mass of one bowl of water, or I can say to increase the temperature of one bowl of water from 0 degrees centigrade to 100 degrees centigrade, some heat was required. Suppose Q1 heat was required. Okay. Now again to increase this full beaker of water from 0 degrees centigrade to 100 degrees centigrade, can I say more heat will be required? Let's say now Q2 heat is required. So what I'm going to say that if temperature increase is same from 0 degree to 100 degrees centigrade in both the cases, can I say the heat required to raise the temperature of any water, what I'm saying, equal increase in temperature can be said as directly proportional to mass of water. Yes or no? If mass of water is more heat will be required to raise the same amount of increase in temperature. Getting my point? Now take the second case. Now what we are going to see, suppose I am taking a mass of water, constant mass. Okay, I am taking a constant mass of water. Suppose this half beaker of water I am taking. So what I am doing in first case, I am increasing the temperature of water from 0 degree centigrade to 10 degree Celsius. Suppose heat required, suppose Q1. Now for the same amount of water, this half beaker, to increase its temperature by 20 degrees Celsius, the heat required was Q2. So obviously Q2 will be greater than Q1. Yes or no? Obviously heat required to make the more increase in temperature will be more. Okay. So what can I say in this case? That if mass is constant, the heat required to raise the temperature is directly proportional to increase in temperature. Yes or no? If more increase in temperature is required, more heat will be required for the same amount of substance. So we have seen 2 things. First, we have seen here that the increase in temperature was constant. Okay. So for say increase in temperature as constant, heat required was directly proportional to the mass of substance. So for more mass of substance, the more heat will be required to increase its temperature by the same means or by the same magnitude as in the previous case. And for the mass as a constant quantity, more heat will be required for more increase in temperature. So these are two things. Okay, so if I combine both these things, I'll get a relation like this. Q is directly proportional to M, and Q is directly proportional to delta theta, where delta theta is the increase in temperature. Delta theta is increase in temperature. And what about M? M is the mass of substance. M is the mass of substance. Okay, so if you remove any proportionality constant, and before removing the proportionality constant, if I combine both these relations, I can write heat required is directly proportional to M as well as delta theta. Yes or no? This thing is clear. So heat required is directly proportional to M as well as increase in temperature, mass as well as increase in temperature of that mass. Okay, so if you remove this proportionality constant, you have to put a constant here. So suppose that constant I am putting as C. I am naming this constant as C. So this is actually the relation. This is the actual relation. So whatever constant I am talking about here, this C will be known as specific heat. What we are going to learn today is the first term. So this constant is known as specific heat. Getting my point? First, what we have learned? We have kept the increase in temperature constant. What we have learned? Heat required is directly proportional to mass. In the second case, we have kept the mass of water constant. And what we have observed? Heat required is directly proportional to increase in temperature. More increase in temperature will require more amount of heat. Done? And when we have combined both the relation, we have put a constant which is known as C and which is defined as the specific heat. Okay, which is defined as the specific heat. So if I write the formula of C from here, can I write C is equals to Q by M delta theta? Yes or no? Q by M delta theta. So this is how specific heat is defined. So before going into the much deeper explanation, we will directly see its definition, that how can you define C. So specific heat is also known as specific heat capacity. Okay, specific heat is same as specific heat capacity. So what is written here? Specific heat capacity or specific heat of a substance is the amount of energy, or you can say amount of heat as well. Amount of energy or heat required to raise the temperature of 1 kg of that substance by 1 degree Celsius. So this is the relation what we are studying. I've already told you in the previous slide. So it is like in place of delta E, we have used Q. So Q by M delta theta. So what it tells that if you put the value of Q, if you put the value of M as 1 kg in this relation, if I put M as 1 kg, delta theta is 1 degree Celsius, what will I get? I'll get C is equals to Q by 1 into 1. Yes or no? 1 was the mass and 1 was the change in temperature. So from this, can I say C is equals to Q? What of energy or heat? So can I define specific heat as the amount of heat required to raise the temperature of 1 kg of substance by 1 degree Celsius? This thing is clear. So specific heat is defined as the amount of energy or heat required to raise the temperature of 1 kg of any substance by how much amount? By 1 degree Celsius. So this thing is clear. So how can you feel this specific heat? Suppose if I say the standard unit of specific heat of water, if I say specific heat of water. So specific heat of water is given by 1 calorie per gram degree Celsius. This is actually the value of specific heat capacity of water. So what does that mean? That 1 calorie is the heat or energy required to raise the temperature of 1 gram of water by how much amount? 1 degree Celsius. 1 degree Celsius. So if I ask you, I have to increase the amount of, or I have to increase the temperature of 10 grams of water. I have to increase the suppose if I'm saying I have to increase the temperature of 1 gram of water by 10 degrees Celsius, suppose. So what will be the energy required? Energy will be specific heat into increase in temperature. So that will be 10 calories. Yes or no? So this is the benefit of defining specific heat, that if you have defined specific heat for any substance, yes or no? If you have defined specific heat for any substance, then you can be able to directly calculate the heat required to raise the temperature by any amount you want. Okay. Clear? So this is specific heat capacity. Now, if I talk about the SI unit of specific heat capacity, what was specific heat capacity? Q by M delta theta. What is Q? Q is energy or heat. So the SI unit of energy or heat is given by joule. You all know. SI unit of mass is kg and SI unit of temperature is Kelvin. So basically SI unit of specific heat capacity is joule per kg Kelvin. Okay, joule per kg per Kelvin. There is also common unit I have already mentioned, which is given by calorie over gram per degree Celsius. So both the units are valid for specific heat capacity. But if I talk about SI unit will be joule per kg per Kelvin. Clear? So I think specific heat capacity or specific heat is clear that it is the amount of energy or heat required to raise the temperature of 1 kg of a substance by how much amount? By 1 degree Celsius. Clear? Done? Okay. Now let's move on to the second term of today, which is thermal conductivity. So what is thermal conductivity? If I give you a basic feel, that thermal conductivity is a measure. It is basically a basis of measure that how easily any substance allows the heat to flow through them. So it is basically a quantity or a measure that measures that how easily can a substance allows the heat to flow through them or to transfer through them. Okay, so that is the basic meaning of thermal conductivity. Okay, so how you can get a much better feel? Suppose, and you already know heat flow takes from hot to cold, yes or no? We have already learned in the previous lecture that heat always flows from hot body to cold body or hot end to cold end of a body. That we have already learned. So how can I get a feel that suppose this is a cold body, this is a hot body. I am attaching or I am joining this body with a iron rod. Suppose this is an iron rod. So what will you observe after 1 minute? After 1 minute, you will observe this cold body will be filled by you as a warm. If I say if you touch your hand on the cold body after 1 minute, you will feel warm in your hands. So what is that warmness? That warmness was due to the transfer of heat from hot body to the cold body via this iron rod or through this iron rod. Suppose if you repeat this experiment, suppose you are repeating this experiment and you are now connecting the hot body with the cold body with the means of a plastic rod, or you can also take a glass rod. Okay, now again give some time for 1 minute, and after 1 minute touch your hand on the cold body. Now you will observe that you will not feel any warmness, okay, or I can say less warmness or less heat in comparison to the case of iron rod. So what is the reason for that? Basically plastic rod or glass rod is a non-metal, okay, and this iron rod is a metal. So can I say, according to the concept of thermal conductivity, that iron rod has a more thermal conductivity? Why I can say this? Because iron rod easily allows the heat to flow through it. While in case of plastic rod or glass rod, it was not allowing the heat to flow through them easily. That's why after 1 minute, when you were touching the cold body in case of iron rod, you were feeling warm or more heat. And when you were touching your hand after 1 minute in the case of plastic rod, you were not feeling that much warm, or you can say you were feeling less heat. Okay, so who was easily able to transfer the heat? Iron rod. So I can say iron rod has a more thermal conductivity than the plastic rod. That's how you classify the material according to their values of thermal conductivity. Basic feel of thermal conductivity is clear, that how easily any substance is able to allow the flow of heat through them is measured by a term which is known as thermal conductivity. Done. So what is the reason for thermal conductivity in metals? That metals have more thermal conductivity than non-metals. So if I write a relation that thermal conductivity thermal conductivity of metals is greater than non-metals. Okay, this is the relation for thermal conductivity. Then now we are watching what is the reason for that. Because in metals there are large number of delocalized electrons. What do you mean by delocalized electrons? Which are free to move. So suppose I am taking a cross section of a conductor or any metal. There are large number of free electrons present here, or large number of delocalized electrons present here. So whenever you touch a hot body at this end and you touch a cold body at this end, suppose this is a metal like iron rod. So as soon as you touch this hot body, that this heat from the hot body will get transferred to the electrons present here, and that electrons by their movement, because they are free to move, so that electrons by their movement will do what? They will transfer the heat to the forward electrons. Yes or no? So the process will go like this. Suppose they have transferred heat here, the hot body. Now this heat will be transferred by the free electrons to the forward electrons. Again, these electrons will transfer the heat to the forward electrons because they are free to move. So they will easily start vibrating and transferring their heat. So that's why the heat is easily transferred from hot part to the cold body via metal or iron rod. So that is the reason for higher thermal conductivity in metals, that they have a large number of delocalized electrons, or you can say the free electrons that are very free to move. So whenever you touch the hot body, that transfer of heat is easily taking place by the free electrons or movement of free electrons. Free electrons are transferring the energy layer by layer and getting into the cold end. This thing is clear? Okay. So now what we are concerned about is the second part, which is non-metals. That what is the reason for thermal conductivity, or I can say less thermal conductivity in case of non-metals. So what is the reason? Basically, they have less number of delocalized electrons. Okay. As these have less number of delocalized electrons, can I say electrons are not easily or not free to move easily? Yes or no? So if they are not easily able to move or not free to move easily, what will happen? Once you connect the hot part of the body to the cold part via non-metal, this is hot, this is a cold body, transfer of energy will not take place at a much higher rate because these electrons are not easily movable. So they will not be able to transfer the heat readily. Instead, in non-metals, what happens? There is something called as phonons. PHONONs. Phonons are a kind of wave. So in case of non-metals, energy is transferred with the help of phonons, or you can say waves. So the transfer of waves is at a lesser rate in comparison to the electrons. Electrons or delocalized electrons transfer the heat more readily in comparison to the phonons. So that's why metals have a higher thermal conductivity in comparison to the non-metals. Clear? Thumbs up, guys. So I think you have got the concept of specific heat as well as the thermal conductivity. So these were the two new terms we are going to learn today. I hope you have get a clear view about what is specific heat or specific heat capacity and what is thermal conductivity. Thumbs up. Okay, let's move forward. Now see what is the actual definition of thermal conductivity. How can we define thermal conductivity? Now see, thermal conductivity can be defined as the rate. Rate means you are calculating its change with respect to something. The rate at which heat is transferred by conduction through a unit cross-section area of a material when a temperature gradient exists perpendicular to the area. So gradient means change in temperature. So whenever any change in temperature is present perpendicular to the cross-sectional area, suppose in this case, this is our cross-sectional area, this one is cross-sectional area, this blue portion. This is the cross-sectional area perpendicular to this cross-sectional area in this direction. Yeah. In this direction, there is a temperature difference. If you can see, this T2 part of the body is made orange. That's showing it as a higher temperature or red hot. And this T1 part of the body, which is having temperature T1, is colder one. So T2 is greater than T1. It is written here. So there is some temperature difference present perpendicular to the cross section. Getting my point? This was the cross section I have shaded with the blue color. Perpendicular to that cross section, there was some temperature difference. Getting my point? So if any temperature difference, which is known as temperature gradient, whenever there is temperature change along the length of a conductor or any material, then that will be defined as a temperature gradient. Okay. So if there is any temperature difference perpendicular to the cross section, then heat is transferred by the conduction method, and that calculation of rate of heat which is transferring is defined as thermal conductivity. So thermal conductivity means if any material has a higher thermal conductivity, it means that it is easily, or I can say more quickly, transferring the heat from hot part of the body to the cold part of the body. And if any substance has a low thermal conductivity, it means that it is not very fastly, or it is transferring the heat very slowly from hot end to the cold end. Although it will transfer some heat, but it will take more time in comparison to the material of high thermal conductivity. Clear? So this is how thermal conductivity is being defined. Suppose if I take an example of copper, and I'm taking an example of insulator like styrofoam. One is copper, another one is styrofoam. Before going into the values, first see what is the SI unit of thermal conductivity. SI unit of thermal conductivity. So SI unit of thermal conductivity is watt per meter Kelvin. Watt per meter Kelvin. So this is the SI unit of thermal conductivity. Okay, you can see what is watt, what is energy per unit time. That is the rate. That's what I was talking about, rate of transferring of energy. That's why it is written as watt here. So now if I are you able to understand the SI unit now? It is watt per meter per Kelvin. Clear? Now if I talk about the thermal conductivity of copper, it is around 400 watt per meter per Kelvin. And if I talk about styrofoam, which is an insulator, it is around 0.03 watt per meter Kelvin. So you can see there is a huge difference, almost 100 times. Copper has a thermal conductivity 100 times in comparison to the styrofoam. Yes or no? So you are clearly observing that copper is easily able to allow the flow of heat through it. Okay, it is easily able to allow the flow of heat through it at a much higher rate. Okay, and if I talk about the vacuum, vacuum has a thermal conductivity of 0. So what does that mean? In vacuum, there is no transfer of heat because thermal conductivity of vacuum is 0. So it will not be able to transfer the heat from the hot part of the body to the cold part of the body. That's why it means. So for metals, what is the conclusion? For metals, thermal conductivity is high in comparison to the non-metals. The reason I have already explained, that was due to the presence of more delocalized electrons. Done? Thumbs up, guys. Yeah, thumbs up if you are enjoying the session. I hope these two terms are clear: specific heat and thermal conductivity. Okay, now we are moving forward. So basically we have already seen the basic meaning of two terms. Now we are going to study some basic questions about that. I think there is no doubt in this topic. Okay, clear? Okay. So now question 1, you can read the question. A beggar wrapped himself with a few layers of newspaper on a cold winter night. So a beggar is sleeping on the road and he has wrapped himself with a few layers of newspaper, and the night is cold winter night. So what is this process helping him? So this helped him to keep himself warm. Due to that wrapping of different layers or few layers of newspaper, he was keeping him warm. So what was the reason for that? First, friction between the layer of newspaper produces heat. Okay. Second option, air trapped between the layers of newspaper is a bad conductor of heat. Okay. Newspaper is a conductor of heat. Okay. Newspaper is at a higher temperature than the temperature of the surrounding. Obviously, this D option is wrong. Obviously, the temperature of outside air on a cold winter night is higher than the temperature of the the current newspaper is at a higher temperature than the temperature of the surrounding. Okay, so that is the correct point, but the reason is different. Point is correct. Yeah. So newspaper is a conductor of heat? No, it is not a conductor. Yeah. So see A option, friction between the layers of newspaper produces heat. No, we can't see any much friction. If you rub two newspaper sheets, you will not observe any significant friction or any significant heat. But that option is not matching. Now see the second option. Air trapped between the layers of newspaper is a bad conductor of heat. Suppose these are the layers of newspaper. Yeah, I am showing the exaggerated view for the explanation purpose. And these are the air particles or air trapped between the newspaper. Yeah, air is present everywhere. So between the spaces of newspaper layers, there is air present. And you know, air is a bad conductor of heat. Air is a bad conductor of heat, or you can say air has a low thermal conductivity. You can also say air has a low thermal conductivity. Suppose this is the man who was sleeping here. This is the man who was sleeping. So this man has a higher temperature than the surrounding. Yes, the normal body temperature is around 37 degrees centigrade. Yes or no? So this temperature is higher in comparison to the surrounding temperature. So when he has wrapped himself with a newspaper, what he has done? He is at a higher temperature than the surrounding, but now heat will not flow into the atmosphere, because if there was no newspaper, heat from the body of person should easily flow from body of the person to the surrounding, from higher temperature or hot body to cold body. This is a basic phenomenon of heat transfer. But yeah, due to the presence of newspaper and air between the newspaper, heat was not able to get transferred into the surrounding easily. That's why the person feels warm, because there is no escape or transfer of heat due to the presence of air, which is a bad conductor of heat, or you can say low thermal conductivity. Low thermal conductivity. So what is the most appropriate answer? Most appropriate answer is option B. Done, guys? Clear? Now see next question. A marble tile would feel cold. Marble tile will feel cold as compared to a wooden tile on a winter morning, because the marble tile. So he's asking the reason that on a winter morning, marble tile feels more colder in comparison to a wooden tile at the same place. So what is the reason for that? Yeah, see one by one. Is a better conductor of heat than wooden tile? Yeah, obviously marble is a good conductor of heat than the wooden tile. Okay. Now second one, is polished while wooden tile is not polished? I don't think that doesn't make any sense. Yeah, polished doesn't make any sense. It makes sense in case of friction only. So there is no need of friction here. Let's see option C. Reflects more heat than wooden tile. Okay. Is a poor conductor of heat than the wooden tile? No, it is a better conductor of heat, not a poor conductor of heat. So what is happening? Marble is a better conductor of heat than the wooden tile. Marble is a better conductor than the wooden tile. So what will happen if it is a better conductor? Can I say this has a more thermal conductivity? If it is a good conductor of heat, I can say thermal conductivity of marble is greater than thermal conductivity of wood. Yes or no? So if marble has a higher temperature in respect to surroundings, it will easily lose the heat. It will easily lose the heat to the surrounding, because it has a higher thermal conductivity. It will allow the flow of heat through it more easily or more rapidly. So in comparison to the wooden floor or wooden tile, marble tile will allow the flow of heat from it to the surrounding and will get cold easily or more rapidly than the wooden tile, because wooden tile will take more time to lose heat because of its low thermal conductivity. So reason is clear. Marble tile has a higher thermal conductivity, or you can say a good conductor of heat or a better conductor of heat. So that will allow the transfer of heat to take place in less time. So that's why marble tile feels colder, because it has lost its heat. It has lost its heat to the surrounding more easily or more rapidly. So that is option A. It is a better conductor, or you can say higher thermal conductivity. That's why its temperature is cold in comparison to the wooden tile. Clear? Now see question 3. Paheli and Boju measured their body temperature. Paheli found her to be 98.6 degree Fahrenheit and Boju recorded 37 degree Celsius. Which of the following statement is true? So this is the temperature scale, basically degree Fahrenheit, degree Celsius. So if you remember the interconversion we have already seen. Yeah, I told you in the denominator measure, keep the difference of boiling point and freezing point at that temperature. So if I talk about Celsius, it was 100 degrees Celsius minus 0 degrees Celsius, boiling minus freezing. In the case of Fahrenheit, it was 212 degree Fahrenheit and minus 32 degree Fahrenheit. Remember, I have already mentioned, or I have already told you, you can also make your temperature scale. I made the Aditya temperature scale in the class. Yes, remember? Okay. So there, what you do, you measure the temperature in degree Celsius minus freezing point. Here, you measure the temperature in degree Fahrenheit minus 32 degree Fahrenheit. So this is the interconversion between degree and Fahrenheit. So see what is given. 98.6 is given and 37 degrees given. So let's put 37 degree here and see what will be its temperature in Fahrenheit. So it will be 37 minus 0 divided by 100. 100 minus 0 will give you 100. Degree Fahrenheit minus 32 degree Fahrenheit divided by 212 minus 32 will give you 180. Okay, so 10 and 10 will cancel out from here. So if I see 18 into 37 just by cross multiply, divide by 10 is equals to temperature in degree Fahrenheit minus 32 degree Fahrenheit. Yes or no? So can I say it will 1.8 into 37 is equals to degree Fahrenheit minus 32 degree Fahrenheit. So if you solve this, you will get degree Fahrenheit temperature as 98.6 degree Fahrenheit. So this is the basic interconversion, how you can do the interconversion. Okay. So 37 degree Celsius is same as the temperature in Fahrenheit as 98 degree Fahrenheit. Now you can easily find the temperature or answer. Pahali has a higher body temperature, no. Lower body temperature, no. Normal body temperature, yeah. Normal body temperature is 37 degrees centigrade. Both are suffering from fever, no. Fever is around 102 degrees Celsius, yeah. So both are having normal temperature because 37 degrees is normal body temperature and 98.6 degree Fahrenheit is also a normal body temperature, which is equal to 37 degrees. We have already seen it. So the correct answer will be option C. Both are having normal body temperature 37 degrees Celsius, or it can also equate it to 98 degree Fahrenheit. Okay. So I hope all is clear. Thumbs up, guys. Specific heat, thermal conductivity, both the terms are clear. Okay. So we are done with today's lecture. I hope you enjoyed the class. Yeah, I hope you enjoyed the class. We have learned the two important quantities, specific heat and thermal conductivity. So if I summarize today's lecture, what was specific heat? Specific heat was the heat required to raise the temperature of 1 kg of any substance by how much amount? By 1 degree Celsius. In that SI unit, we joule per kg per Kelvin. It was the temperature here. Getting my point? Yeah. So we were studying. Okay, let's continue. Yeah, over here. So we are revising the conclusion of the class that what was specific heat? Specific heat was the energy required to raise the temperature of 1 kg of any substance by how much amount? By 1 degree Celsius, and the SI unit of specific heat was joule per kg per Kelvin, or you can also say calorie per gram per degree Celsius. And we have seen what is thermal conductivity. Thermal conductivity is a measure of material or a substance that how easily a substance is able to measure the heat. How easily a substance is able to measure the heat transfer. Okay, so I hope every concept, specific heat and thermal conductivity is clear to you. I hope you enjoyed the lecture. So in case of any doubt, please refer to the askIITians website. It is having a doubt forum. Yeah, it is having a doubt forum. You can post your doubts there and it will be solved by the experts. Okay, so we'll end the class here. Thank you so much. Have a nice day. Stay safe and enjoy.